So folks, in this video we're going to introduce our last two vector operations, and those are going to be the divergence and the curl operations. So these will be operators or operations that we can do on vectors, and we'll look at both of those. So our objectives are to define both the divergence and curl. Then we'll learn how to calculate each of those after we've defined them for both vector fields and at particular points within a vector field. Then we'll develop an intuition for curl and divergence. So let me just say that in this section, let's assume that we are in R3. So when I give a function f, we're going to assume that it maps from R3 to R. So it takes three input variables and it outputs a single variable. And if I talk about a vector field, then it takes a point in R3 and maps it to a vector in R3. And all of everything I'm doing with divergence in this video can be extended to any number of dimensions that you wish, 1, 2, 3, 4, and higher. But the curl will only be defined for 3 dimensions, and that's really where we've been operating for this last part of the course. And so that's why I'm choosing to do it this way. So here's some meaningless but useful notational shortcuts that we're going to look at. So we're going to define this guy right here, and we've seen him before. We're going to call him the del operator. And the del operator is sort of a meaningless notational choice that we make, but it really helps condense our notation. So we're going to think about the del operator as being the vector of whose entries are these partial derivative operators sitting inside of here. So we've got the partial derivative with respect to the first component function in the first position, the partial derivative with respect to the second component function in the second position, and likewise. So if we had higher dimensions, we would write it that way. Why do I call this meaningless? Well, because we've defined a vector as something that has both a magnitude and direction, and this has neither magnitude nor direction. It's just in place of the components where we normally have the coordinates of a vector, or we normally have the coordinate functions for a vector, I've put these operators. And that's why we think of it as meaningless notation, but it does help us write a lot of these ideas in a much more condensed way. So we've already seen this before. In fact, we called it the nabla symbol, and we used it with a vector, with a function, a real valued function, to symbolize the gradient of that function. So I want to show you how we could use this same del operator notation to rewrite our way of thinking, or to think about our gradient. So the del operator I replace with partial x, partial y, partial z, and then I'm going to apply that to the scalar valued function f. But because f is just a scalar, we know that we can distribute the scalar to each of the components, just like we would if this was an actual vector. We could distribute that f through, and so we'd get our usual notation for the gradient: partial f, partial x, partial f, partial y, partial f, partial z. And as soon as we've applied this del operator to the scalar function f, notice that we are back to having an actual vector. In that we have these 3 component functions, and we could then evaluate those pointwise. Okay. So for divergence, here I've selected that we've got a vector field of 3 component functions. We're going to go ahead and define our divergence to be what follows. Now, by the way, I should have said this was R3. I'll fix that for your notes. But you can extend this to higher notation. But here we go. Let's go ahead and define our divergence. So we're going to use, to shortcut divergence, we're going to use this notation, del dot f. So we could read that as del dot f is how we would read that notation there. And this is how we're going to shortcut the expression for divergence. And to do that, we're going to take the del operator, partial x, comma partial y, comma partial z, and we're going to dot it with this vector field, which has these component functions f, g, and h. And so if we actually perform this dot product, we get our expression for divergence. So partial f, partial x, it's a dot product, so plus partial g, partial y, plus partial h, partial z, doing the ordinary dot product that we've always done. The only difference is that we've got, instead of a vector right here to do the dot product with, we've got this vector looking thing that has the derivative operators, but we still perform the dot product as we always have. So again, this notation itself is meaningless. It has this meaningless del vector. So this notation is really meaningless, but it's a shortcut for remembering the formula for divergence. So what do you need to know? You need to know that this is equal to this. Okay? So let's say a couple things here. How would we read this? If the divergence of the vector field is 0, and that is the number 0 there, folks, right? Because we obtained it by doing a dot product. If the divergence of a vector field is 0, then we say that the vector field is source-free. Or another way of saying that, we could say that the vector field is incompressible. Okay. And I just want to interpret this because we've seen the 2D divergence before when we looked at Green's theorem. We rewrote our flux line integrals as two-dimensional divergence integrals. And I just want to remind ourselves what we saw in that. When we say that the vector field is source-free or incompressible, what we mean is there are no sources or sinks in that vector field. So before we get into some more intuitive examples, let's just do the rote calculations here. So here we've got this vector field f, and I've given it by these three component functions here, and it looks like, 1, 2, 3. It's a little hard to see those commas. We get these three component functions here. So the function f of x, y, z is the function x squared y. The function g of x, y, z is the function x plus y, and the function h of x, y, z is the function y minus z squared plus the cosine of x. Okay, so we're asked to compute what? So how do we read this, folks? We're asked to compute del dot f. That's one way to say it. The other way to say it is we're asked to compute the divergence of this vector field f. So the mnemonic that we've given with this del operator reminds us how to do the computation. We will take partial x, comma partial y, comma partial z, and we're going to apply that to the functions f, g, and h. And so let's actually do that dot product there. So if we do that dot product, if we take the partial derivative of the first component function with respect to x, I get 2xy, excuse me, this is a dot product, I get 2xy plus, if I take the partial derivative of the second component function, folks, I have a mistake here when I copied this should have been a z. When I take the partial derivative of the second component function with respect to the variable y, I get plus 0, plus when I take the partial derivative of the third component function with respect to z, I get minus 2z, and so we can rewrite this as 2xy minus 2z, and this gives us the divergence of this vector field. Remember, you can think of divergence as a scalar function that tells us how much any point in the vector field in that space is behaving like a sink or a source. So in fact, let's go ahead and do a computation here. So we'd like to compute the divergence of f at the point 1, 2, 3. So what I'm doing here, folks, is without defining everything, I'm going ahead and showing you, well, this is one way of talking about divergence. Here's another way of talking about the divergence of a vector field. It's just another notation that you'll sometimes see, and we're going to do this at the point 1, 2, 3. So we've already said that the divergence, and we'll just recopy here for practicing the notation, the divergence of f at any point is 2xy minus 2z. And so if we want to compute the divergence of f at the point 1, 2, 3, that's going to be 2 times 1 times 2 minus 2 times 3, and that comes out to be negative 2. So the divergence at the point 1, 2, 3 of our vector field f is negative 2, which means that that for any small area or small region placed around the point 1, 2, 3, if we look at the vectors in that small region, we would have sort of a net influx of vectors as opposed to a net outflux. That's because the divergence there is negative, meaning that around the point 1, 2, 3, the vector field is behaving more like a sink than it is like a source. So folks, the last thing I want to do is just help develop a little bit of intuition for vector fields. And so I've got these two vector fields here. I didn't label them. Let's call this the vector field F here and the vector field G here. And you can see that I've sketched these vector fields in R3. Now, something I would warn you of is oftentimes you cannot determine the divergence of a vector field just from looking at it. And I've chosen these examples very specifically because I think it's possible to determine what we mean by the divergence at any point. So for this first vector field F here, I want you to determine the sign on the divergence. So we're going to figure out what the sign on the divergence of F is. And over here we'll do the same thing. We'll determine the sign on the divergence of G. And I'm just practicing these two different ways of writing divergence. And I think that you can observe this from this sketch here. And if not, I'm sorry, it's a product of my poor ability to build one of these. But if you were to let's first take any point in the vector field. Maybe this is the point here, this point right here. And if you were to put a little infinitesimally small cube around that point, or an infinitesimally small ball around that point, would you say that region is behaving more like a sink or a source? And it's hard to tell here because of these vectors that I've drawn in the vector field. There are some small vectors coming in I want you to imagine that is going into the box, but you have larger vectors coming out of the box than going in. And so we would say that this region right here is behaving more like a source than it is a sink. And that is actually true for all other points in this vector field. In fact, if you were to compute the divergence of this vector field F here, you'd find that it's always positive, which means that every single point is behaving like a source. And so the divergence of F here is greater than 0. Again, this isn't the best example, this is a good example, but it's not one that you'll be able to apply to all vector fields. In general, the vector fields will be so complicated that you can't look at the entire vector field and determine the divergence at any point. Even if you go to analyze specific points, you may not be able to determine the divergence just from looking at it. So these were specifically selected because I hoped that you'd be able to determine the divergence. So let's do the same thing here. If we were to again take, say, this point right here, maybe that's this x-coordinate, this y-coordinate, this z-coordinate. So if we go out here and go up to here to get to this point right here, sitting somewhere in 3 space, if we were to construct a little open ball around that point, and we thought about, well, do we have more vectors coming in or going out? My hope is, and it's a little hard to tell, my hope is that you'd see that you have sort of, in terms of length, these vectors are a little bit longer, and you have fewer vectors coming out of that region here. So my hope is that you can determine that the divergence here is negative. Folks, if you don't feel comfortable determining whether the divergence is positive or negative at a given point for a vector field, I don't feel bad about that. It's not something I'm going to ask you to do a whole lot of, so just keep working on it, but it's not an essential part of doing the calculations. But I think it is helpful for developing our intuition for what do we mean by the divergence. So the divergence of a vector field is this expression right here, which we think of as a way of computing whether a particular point is behaving like a source or a sink, depending upon the sign of the divergence. So folks, the last thing I want to do is just make a statement about how this del operator works. If F is a 3D vector field, then the vector field itself takes points in R3 and maps them to vectors in R3. We've done that before. That is, F maps a point to a vector. But the divergence of F is a new function, and it's in fact a scalar function, where we think of taking points in R3, and we think of those points as living inside of our vector field. But we take points in R3, and we assign a number to them that corresponds to the divergence of the vector field at that point. So keep in mind that this divergence of F is itself a scalar valued function, and it takes points in R3, maps them to R, so in fact the graph of the divergence we can't actually sketch because it lives in R4. But again, the way we interpret it is we go to every single point in our vector field and determine the divergence at that point, which would be a number corresponding to whether or not that point's behaving like a sink or a source, and to what degree. So folks, that about wraps us up with divergence. We'll still do a little bit more work with it when we get to class, but in the next video we'll start looking at the curl. So I'll see you there.